All right, welcome to part two, Intro to FRC Programming. This is an intro class, so we're going to get you into, you don't need any experience with programming at all to start with this class. The advanced class, you'll have to have this class before you can do the advanced class. So, this is based on the 2023 FRC competition code base that we are working on. It's an introduction. It focuses on Java-based programming. It's the most simplistic for students to pick up, and this is what we actually teach. You will need to learn a lot more to make your robot wow than what this course is going to teach you. This course will teach you how to make your robot move, and it'll teach you how to make your robot cross the line, which is a bare minimum that we want to see from robots in competition. Cross the line, get those points. You are not the first to learn this programming. You will not be the last. So ask lots of questions, and once you're in the know, answer lots of questions. Okay? It's all of our responsibility to help onboard the next generation of coders. So, I'm Roger Johnson, and I'm the assistant coach for FRC Team 5484, and I do basically the programming and argue with the engineers all the time. No, you can't plate that there. Where am I going to put the wire for that? And all those sort of different things. And based on that, I'd like to introduce you to Mr. Ebersol, our head coach.
Hi, I'm Dave Ebersol. I'm the head coach at 5484. We started this team this will be our 10th year. And
10th year.
we've had a bunch of problems with programming and CAD. And during COVID, we utilized that off season to really hammer in the things that we didn't understand with programming and with CAD. In the last couple of years, right out of COVID, we've had our first Swerve bot and our first fully CADed robot that we were able to machine from machines we have in-house. So this is just now creating the legacy to propel those systems forward to make sure they don't go away.
Yeah. So when I started with the team, when the team was founded, I was mostly just support. I just helped them wherever they needed. And then that evolved due to necessity to the programming. Now, fortunately for me, I had a base in programming even before the team. I've been programming for over 20 years. So it's like, all right, this shouldn't be too hard. And then I cried. All programming is easy in the basics. It's all easy in the basics. When you're trying to actually achieve something, especially when you get a game goal, and you're like, all right, how do I make the robot do this with this parts, with what FRC lets me do? That was my biggest frustration. It's like, why can't I use this and why can't I use that? Those are not FRC approved parts. You can't use those things.
From the engineering perspective, my biggest problem was, why can't you just make the arm do what I'm thinking? What do you mean I need sensors? This is ridiculous.
So to have an effective robot, we have to have effective sensors, and we have to be able to program and utilize those effectively.
And we have to engineer with those sensors in mind.
Yes.
That's been the number one bottleneck that we've had.
You cannot let your programming be the afterthought.
Yes.
Because you will have a huge problem making it actually work.
Which is literally the way that we ran the team. Was the robot is built, then programming gets it, and you guys have to figure out what to do with the robot we gave you.
Right.
And that is the wrong way to do it.
We had our robot last year was over 90% autonomous, meaning even the drivers driving it, it was a suggestion for the robot. The robot, when they were taking the controls and controlling the arm, they were suggesting to the robot to accomplish that. The robot actually decided based on circumstances whether it would follow that rule. So the robot was really, it's like the drivers that even during teleop, the drivers were giving it suggestions and it would decide what to do to actually accomplish that suggestion.
For example, the biggest one of that was the anti-tipping code.
There was
a lot of like stop and go. and the robot would decide if it was too much of a velocity to increase that fast, so it would either ramp up or slow down based on the circumstance at the time.
Yeah.
That was pretty cool.
So if the robot started tipping, and the driver's like, "I want to drive further," and the robot's like, "Oh, no, we're gonna go this way because I'm about to fall over." So it ran itself, and that is where we really want to go with our robots. We want our robots to be able to decide what is best for them to accomplish the goal, while the drivers are telling it, "I would like you to do this," and then the robot figures out how to accomplish that. That is what we're going to learn in the advanced class. We're not going to learn that today. Again, we're learning how to make our robot move. That's the number one goal. With all starting teams, that is the hardest part, taking the robot and making it actually move. Sound good? All right. So, the first step in all of this is we have to have all the right software and tools to actually work on our robot. There are two sets of tools that we have to install to work with our robot. First, we have the National Instruments game tools, and then we have the WPI library programming tools. These are the two pieces of software that we need minimum to actually work on our robot. You can find all of these steps, all of this information in the docs.wpilib.org website. So if you go to that website, that's not what I want. When you go to this website, what you're actually going to find is WPI library. WPI library is actually programmed by a college, WPI, and they're the ones that actually have programmed all of the base systems that actually make the game what it is, including the FMS, which is the field management system that actually manages all the robots during competition. So, fun fact, when you program your robot and you say, "Hey, I'm going to give it commands from my driver station to my robot," when you're in the shop, your computer is directly relating to your robot. When you get to competition, you don't get to talk to your robot anymore. Only the field does. So your command station, your driver station, will actually take all of its commands and desires, what it wants the robot to do, give it to FMS, the field management system, and the field management system then relays it to your robot. The reason they act as this middleman is so they can disable your robot or do whatever they need to your robot and actually monitor your robot during the competition. That's how they know if your robot goes crazy, they can just kill it and you have no say in it. If you had issues with your robot, they can actually look at the tablets and see what exactly the issue was. They don't necessarily know why it happened, but they can see what the issue was. And then they have control. They can say when the game starts, they say when the game ends, and all of that stuff. This is all programmed by WPI and the WPI library. They have made it possible for beginning programmers to program the robots without everyone quitting FRC. That's the truth. Because before this library, you had to program your robot basically from scratch. You literally had to program motor controllers. You had to program the actual signals. No one does that anymore. And because in real life, we don't do that in real life. If you decide to be a programmer in your real life and you go up, you're not going to have to program unless you invented something brand new. You're not going to have to invent your code base. You're going to use a code base that's been programmed for you. So WPI has everything that you could possibly want to know documented in this library website. It even has a section to building your robot. And then step 2 is the one that we're focusing on today, is the software. So the third link down, you see installing the FRC game tools. So we're going to click on that. And it says, hey, you need to download the FRC game tools from National Instruments. So you click on the FRC game tools, and you're going to download the latest patch. So you guys go ahead and download that. What you're going to get from that download is the Robo Rio Imager. Now, from the last class, we learned the Robo Rio is the brains of our computer. It's that square gray box made by National Instruments. That is everything that is your robot. All of the intelligence of your robot is in that box right there. It's also going to download and install the FRC driver station, and it's going to install the simulation and other tools that you use throughout your robots, including like programming your radio, programming all of these other different things. It's all part of that. Here's a direct link to that download if for those that are watching on the stream that you need to get to. But again, you can go to step 2 in the WPI docs and download it. And this is what you're going to get. Install software, installing FRC tools, download the game tools, and once you run it, you're going to get the package. We'll install it. Yeah, I just install all the defaults. Install all the defaults. Now, let me show you this real quick. If you have it installed and you have, there's an update, if you launch the package manager, it's actually going to show you any updates that have been issued. You need to do this throughout your build build season and throughout competition season, because as bugs are discovered, they will patch them, and you want to make sure you don't have a bug of known origin in your code when you actually go to play the games. An example especially is the driver station. They have discovered bugs in the driver station, and they patched it right before the very first competition, and it turns out that a lot of teams we were competing with did not get the updated driver station. So they actually had that bug during competition, which is really bad. Okay, so the next part, once all of those tools are finished and downloaded and installed, the next tools that we're going to download are the WPI library tools. Now, WPI no longer actually stores those tools on their website themselves. They actually host them in GitHub. So you can directly navigate to GitHub if you want to get it from there. But it includes all of the libraries, all of the tools like PowerWeaver, Shuffleboard, the Robo Builder, SysID, Glass, Outline Viewer, VS Code. It includes an option to download and install and configure VS Code for you also. All the extensions and dependencies that you need for programming our robot. So in that step 2 again, installing software, we go to the next link, which is the WPI library. And you'll see a little link that says GitHub. It'll take you directly to that GitHub and the latest release that is available for you to download. When you scroll all the way to the bottom, you will find the Windows 64-bit version of the library that you want to download. Simply click on that, and it will download. Once it is finished downloading, it's an ISO file, so it's actually a container. And when you double click on it, it's actually going to create a virtual DVD-ROM on your computer. So you'll see it pop up as like a new DVD on your computer, even though your computer may not have a DVD drive in it, it shows up like that. And it has all of the tools, all of the software. You run the WPI library installer, open it, run it. This is actually the 2002 or 2022 version. Yes, you're going to download the latest version. Click on that. From here, it'll ask you, do you want it to install Visual Studio Code for you? Say yes, download it for this computer. It's going to fill up that little bar. Once that bar is full, you get the next button. Sat there on the next button for a while for some reason. Apparently it wasn't paying attention. Click next, and then from that point it will install all of those tools for you. This is to get the library, the WPI tools, and it'll install and configure Visual Studio for you if you wanted to. It's actually Visual Studio Code. If you have Visual Studio Professional or any of those higher ends, you can absolutely use that too. If you want to stick with the tools that everyone's familiar with, which I highly recommend, especially if you need help, use the Visual Studio Code for your robot. You can actually have both installed if you want, but use Visual Studio Code if you want help. It's just easier for people to help you if you're using the common set of tools. And then you click Finish. The next component that we want to install and work on is GitHub. GitHub is a free-to-use cloud service that is a repository for our code. The great thing about it is it'll store all the code that we are working on We can create multiple repositories, have multiple collaborators working on it at the same time, and it stores versions. So every time someone updates the code, it's creating a new version of the code. So if somebody went in and accidentally deleted a whole bunch of stuff, we can actually go to previous versions of the code and restore it. So we can actually get a very good history about what has been altered and who altered it. So it's great for keeping all of your code, and it is common courtesy and practice in FRC that at the end of your build season, that you make your code public for other teams, so they can see your code and how you accomplished your tasks. It's good practice. Now I will tell you that we actually make our code public from the very get-go. Our code's always public for any team that actually wants to go and look at it. And if they want to copy it, rock on, copy it. It works for us. Now you always have to alter it to meet your robot's parameters, but our code is always available for anyone to access. Yep.
It's not just for alternation reason. If you want to use the same code base for the next season, considering it was made before build date, you have to put the rules.
Yeah, per the rules. Yeah. Yeah. You will find that a lot of teams do not make their code public, or at least they do not publish how to easily get to it, or it's under an obscure name, so you can't find it. One of the two. We actually make ours very, very easy to find. It's literally FRC Team 5484. Real easy to find. Let me actually demonstrate what our GitHub is for our team. So if we open up here, we go to GitHub. And when we sign into GitHub, everyone has a personal account in GitHub, right? When you guys go, we're going to go through and I'm going to have you guys all create accounts in GitHub. You're going to create it under your personal email address. You are welcome to use your school email address if you need to, but I recommend you use a personal. That way it's always yours even after you leave school. I've seen a lot of students create it with their student account and then lose access to everything once they left the school. So try to, if you can, if your school rules allow you to, try to use your own personal email account to create a GitHub account. Once you do, you will have what you call repositories. Repositories are all the different projects that you are working on in your system. So if I switch to a team repository, the FRC Team 5484, these are all the repositories for the team FRC 5484. I have public archives, public, and I don't actually know if I have any that are private. Sometimes I just create a junk repository just for testing purposes. I mark it private. That is likely not working code, and I don't want someone to try to copy code that's not working. So sometimes I'll make that private. But here we can see our 2023 FRC code base. So if I go into that, this is actually all of the code for that robot. So everything that makes that robot do what it does is listed here. And as somebody else, I can simply go and download this code and run it on my robot. Now again, you gotta set it up to meet the parameters of your robot, but it is fully functional code that anyone can use. That's what a repository is. So we make a repository for every project we are working on, and it stores multiple copies. It tells us when something has last been updated. So if we go into main here, robot, constants, which is the thing we update the most, it was last updated 3 months ago. Yeah, that was during competition. So last time it got updated was during competition. That would have been state. Yeah, last time we updated was state competition. And that's what GitHub is. Does everyone understand? So GitHub's a repository to store all of our code, so we actually know what it is that's, or we have a place to store all of this information from year to year. What I'm going to do for all of us today is I'm going to create a repository for us all to play with. So let's go into actually creating a new repository. I'm going to go to our team. I'm going to create a new repository. Let's name this Intro to Programming. I'm going to make this public. And I'm going to create this repository. All right, so now the next part of GitHub, to access all of these repositories, you have to learn command line and all of the Git commands to get and push code and do all of those things. All right, just kidding. You don't have to actually do all of that. There's a much easier way to use GitHub. There's a tool called GitHub Desktop. It is a GUI for GitHub. So if you go to GitHub Desktop and download GitHub Desktop, eventually it'll launch. This is GitHub Desktop. And what we have in the top left is the current project that we are working on, the branch we are working on, and its latest updates. I can click, if I'm not sure I have the latest version of this, I can click fetch and it'll tell me if I have the latest version of this code. Any changes I make to my code base will populate in this changes form right here. So we can review what has been changed, accept them, and commit them to main, and then we can push it back up to the repository and it updates the code in the repository. All GUI based, no commands we have to learn. So much easier to use. Actually, before I do that, first thing I want to do is clone. So I created a new repository. The first thing I want to do is actually clone this repository to my computer so I can actively work on it. So I go add, I'm going to clone a repository, and I'm going to do the FRC team 5484 / intro to programming. All right, it's not letting me select it for some reason. Click clone. There it goes. And it's cloning. So now I have a local copy of this on my computer, and I can see my current repository is Intro to Programming. So step one for using GitHub is to go and register. So you're going to open up a web browser, go to https github.com, sign up. And I highly recommend you use your personal email account to sign up with. You don't ever want a programmer who's just programming in the background and is not uploading your code. Because if you ever get to a point where, and I've seen this at competition, the programmer couldn't make it to that competition and no one had the current version of his code. And I've literally had to sit there with the team and rebuild the entire code base for them at competition because they couldn't get a copy of the current code that was on their programmer's laptop. Absolutely. Yes. As long as you have permissions to the library. So you have to get permissions to the library. So the repository. So as soon as you guys register, what I'm going to do is add your accounts, all of your accounts, to that Intro to Programming folder. So you guys will have permissions to upload, and we're all going to like play with and upload code to that repository. Recommendations when doing this: create an organization for your team. I have seen lots of GitHubs for teams that were in students' personal accounts. That is a very bad thing to do. Just like if for your company, you have an employee and all of your intellectual properties in that employee's personal Google Drive account. That would be a very bad thing. You want an institutionalized instance of your team, and then give people permission to that institution. That way, the institution can easily be controlled by multiple people, and multiple people are admins of the institution, right? So Dave is an admin of our institution. I'm an admin of our institution. If I go away, Dave can easily still manage the institution and add somebody else if he needs to, so on and so forth. Create a repository for each season, and add the students' personal accounts as a collaborator to those seasons, right? That way we have control over what students are making changes to the code. Anybody, if you make it public, anybody can access the code, but only your collaborators have the ability to upload changes to the code. And when the season ends, set the repository to archive. The main reason of setting something to an archive is it sets it as read-only. So no one can no longer upload changes to that repository. Like the 2023, I need at this point to go in and set it to archive. So no one makes any changes to it from this point forward. You can, if for some reason you set it to archive, you can bring it back out of archive, make it not read-only anymore. If, let's say, we wanted to try out, let's say, Falcons on a robot, and we literally take off the Neos and put Falcons on, we can take it out of archive and do that. But my recommendation is to copy all that code, make a new repository to play with, and then do it in that. But setting it to archive doesn't mean you can't ever get into it again. It's kind of a safety to make sure someone doesn't accidentally play with the code and screw it up. GitHub Desktop is a visual representation of GitHub. So we don't have to learn all of the command lines for actually pulling down code, uploading code, and all of that. It just makes it much easier. We are visual-based people, and a lot of people who say, oh no, the command line is the best way to go, just feel really geeky and feel like they're hacking when they're using command line to do things. We have Windows for a reason. No one here is running their entire system on command line. They use Windows. So let's use the Windows version of GitHub so it's easier for us to interact with, especially for new students. All right, now that we have our tools installed, we have the National Instruments tools, the WPI library tools. Everything that we're going to be using to program our robot is part of Visual Studio Code. Now, Visual Studio Code is actually a free IDE, integrated development environment that you can use for tons and tons of projects. And come to think of it, I've been building custom firmware for my 3D printer using Visual Studio Code, and I wonder if that did something to the extension library on WPI, come to think of it now. But Visual Studio Code can be used for tons of things, not just robotics. Anything you're programming, you can use Visual Studio Code to actually program. It's missing a lot of tools that you will get in like Visual Studio's Professional that you would find in professional environments, but it is free and can be used for really any project. There is a custom extension made for Visual Studio's Code by WPI to extend all of the robot items and commands into Visual Studio, so you don't actually have to know all of the commands to actually use the tools, which is really, really nice. So this is Visual Studio Code that we installed. At the top left of Visual Studio Code, you're going to find this big W when you launch it from the actual launch icon. Let me show you that. So when you go into your computer, you're going to see this little 2023 WPI VS Code. There's also a visual, which is not showing up in the search list right now. There's a Visual Studio actual base that's installed. The one you want to launch is this 2023 WPI library VS Code. The reason you want to launch that one is when you launch that one, it will launch with the extension enabled and running. So we launch that guy, and it opens up into our Visual Code. By default, when you open up that application, it's going to open up into the very last code base that you were working on. So whenever you launch that during the build season, it is going to launch directly into your code base that you've been working on. Keep that in mind. If you're working with multiple different code bases that year, make sure you know you're in which one you're in when you're doing that. Last year we were actually working on a whole bunch of different versions of Swerve, and I kept getting confused about which one I was actually in and overriding settings in another one. We had a Rev Swerve, we had SDS Swerve, and then we had our actual competition code, and I kept getting the projects confused because it just opened up and I start working on it and sometimes broke things. So make sure you understand when it launches, it'll launch the very last thing you opened is what it's going to launch into. But that up in that corner is you're going to find that W that has all the command applets for actually doing something in your code. Let's go back to our sandbox here. So something as simple as creating a project, and you guys can actually follow along with this. Let's just create a new robot project in Visual Studio. So launch Visual Studios using that icon, and that W in that top right corner, you want to click that W, and it's going to open up all of these commands that you have access to. The easiest way, and it's actually, there's even more commands than this, and it's not even showing you all of them. The easiest way to get to the command is, what am I trying to do? I want to create a project. You start typing, it'll narrow down that list for what it is you want to actually do. And let's go ahead and click on Create a New Project. And we're going to get this screen. This screen is going to ask us all of the parameters that applies to our robot, right? So the very first one is select a project type. So if you click on select a project type, it's going to say, do you want a template or an example? They have tons of example codes that are pre-programmed and pretty much ready to go, other than setting up your robot's properties. And then they have templates of setting up your code base for what you're actually programming with. Let's start off with, no, we're all going to do the same thing. We're going to start off with a template. So let's select template. And then it asks, what programming language do you actually want to program in? We are going to be learning Java. The one below is C++. We're going to be programming Java, so select Java. And it's okay, if you select the wrong thing, you can go back down to here and change it to another selection. And then we're going to start off with the easiest to program robot, which is timed robot. Timed robot is the easiest to program with, so I'm going to click timed robot. The next thing is, where do you want this folder to be? Well, I want this folder to be probably, I'm going to go into my documents, create a new folder, robot code. I'm going to create a folder that all my code for all the stuff that I'm programming, I'm going to put it inside a folder. You can name the folder whatever you want, just so you know it's something that you want to use to store all your code that you're working with. So I want all of the code that I'm going to be working on to be stored in a folder called robot code. If you're only ever working on one, you could just throw it in documents if you want to. Heck, you could throw it on your desktop if you want to. It doesn't really matter where you put it. And then says, what is the name of this project? Let's call this my first robot. You can name it whatever you want. And then it's going to ask you, what is the team number? What is the team number for your robot? You must put your team number in here, okay? There is a way to change it, and that's something we'll show in the advanced programming. But for now, you want to put in what your team number is. Our team number is 5484. And then we're just going to click Generate Project. No. It's needed for simulation and testing support. Once we click that button, it's going to ask us, do you want to open it in this window or do you want to open it in a new window? I personally always say open it in a new window. And then I can close the other one. Now, I actually have my code. And let me do something real quick here. I should have done this earlier. Should make it a bit easier to read now. And you see here your project and all the files that are part of your project. The very first thing Visual Studios is going to do is build your project to make sure it has all the files it needs. This is the thing that mine, earlier, not on the recording, but here in class, mine was not working. So I had to work around it for the moment. It would not build. Here I can see build successful. All the components that I need are ready to go and working. Does everybody see that part? All right, so we have our first basis with that. And the one thing that you're going to be doing in your code all the time, you're going to use that little W there at the top right. You're going to click on it, and you're going to click on the Build Robot Code applet. And that will actually run through and build your code. Every time you make a change, anytime you're working with it, you want to build often to make sure you haven't done something that breaks it. Okay? Here's one thing to understand though. Because it built doesn't mean you have perfect code. By far does not mean that. It means your syntax is correct and you haven't deleted something that wasn't supposed to be deleted. That's all it means. Your robot code could absolutely still crash through walls at that point. It does not tell you you have logical errors. The hardest part about once you learn the syntax of robot code, and the syntax of robot code is the language, the grammar. So the grammar of our programming, once you have that down, all of your time is spent trying to figure out the logic of making it do what you want it to do. So you'll always build, throw it to the code, or throw it to the robot, and it doesn't work, and you have to figure out why. So that's where you're going to get it. All of the common ones you need are here, including deploy robot code. Now you're not going to be able to run this right now. The deploy robot code, what it does is it actually will take your robot code and push it, build it, and push it to the robot. It actually will deploy it to your robot. But your programming laptop has to be connected to the robot in order to deploy it. Now that's connected via either USB, so directly connected to it, or you're pushing it to the radio. And that the only time you can push through the radio is when your robot's in the shop. Once you're at competition, the only way to push new code is to plug it in. And you will see often when we are coming back from the field and we need to make a programming change, there's not much time. So literally as one person's pushing the cart, another person's grabbing the cable out, plugging into the Robo Rio, turning the robot on. As we're walking to the pit, plugging it into the laptop, all of us walking at the same time while we're doing this and pushing new code to the robot as we go. It actually happens on our way to the field more than it happens usually leaving the field. But there's been times we've been literally standing in line to get onto the field, and we're pushing code right there in line. That is not best practice, but it's competition and it's what happens. So deploying is how we deploy our code. There's a few more applets that I'm going to introduce you to that are really important for the basics, and we'll get into that here in a second. So the common ones, build, for building the code, deploy. We have vendor libraries where we'll manage our vendor libraries. Vendor libraries is the different hardware that we put onto our robot. They actually have their own set of programming instructions. And we can actually go and grab those instructions and integrate them into our projects. A very common one is if you're using the CTRE products, they have a library for all of the hardware they make. If you're using Robotics, they have a library for all of the hardware they're making. Most of the big manufacturers that make something for FRC has a library specifically for FRC to use their products in your code. So you don't have to invent anything from scratch. It's pre-built and ready for you to use. Then we have to check the WPI library for updates. You want to do this often during build season. During build season, you want to check often that there is an update. During competition season, check it at the beginning of every competition. Every competition. Now, I would recommend that once you have built or you've checked for updates, unless there's a critical update you're experiencing, I would not update your library during competition. And I'm speaking from personal experience. There was an update that came out in the middle of one of our comps, and I installed it, and it broke our code. So the new update to fix a bug had a new bug that particularly applied to us. So be careful about when you're installing those updates, but in general, they're safe, and they're literally there to get rid of bugs that have been discovered. The beginning of this last year, there was a huge bug where the controllers kept not showing up on the driver station. And you would have to unplug the controllers and plug them back in order to get them to actually work. So they came out with an update that actually fixed that issue. And the number one, which is create a new project. Whenever we're working on something, we create a new project. If you want to experiment on your robot, don't do it with your base code. Create a new project and experiment with it on a separate project so you don't ruin what you know works. That's a very, very important aspect. So, now that we know all of the tools, let's learn actually about some of programming basics. So, what is a programming language? A programming language is a set of human readable instructions. Literally, we use programming languages to tell computers what to do, but computers don't follow English instructions like we do. They use machine code. It's just a big set of ones and zeros to tell it literally everything our robots are doing is doing based on ones and zeros, on or off. It's funny to think about that. Everything we do in life with computers is based on turning a switch on and off. I made it really simple, but it's literally that. It's transistors on processors that turn on and off. Everything we do, watching, streaming, recording of this, programming robots that do amazing things just by using on and off switches. Trillions and trillions of on and off switches, but they're on and off switches. What we have to do is take that machine code and compile it, or that human code and compile it into machine code so the machine can actually use it. The problem I was having earlier is I couldn't build. What building is actually doing is it's compiling it down into machine code. And mine wasn't working. I couldn't actually compile down into machine code. The two most often used languages in FRC is Java and C++. Those are the two most used languages. Now there are advantages and disadvantages to both. C++ has an advantage that it runs natively on the RoboRio with no virtualization, no additional hardware utilization. It's a very efficient language on the RoboRio, but it's incredibly hard to program it. C++ is not for the light of heart. Those are people that are interested in just the aspect of programming in itself. C++ is great for that. For everyone else, we use Java. Java is way easier to use, way easier to understand, and it actually is the same code base that other languages use, like Microsoft's .NET framework uses the same layout and syntax that Java does. So it's widespread. There's more people that understand Java than C++ in general. And there's a little performance hit with Java, but especially with the RoboRio 2, we're not even getting close to peaking what the RoboRio can do as far as performance-wise. So that's not really an issue. There is a third option called LabVIEW. LabVIEW is actually made by National Instruments themselves, and it's made for non-programmers. It is based on block code. So you can actually take little blocks, like you guys are familiar with, or you've tried Scratch and things like that. It works basically like that. It's made for people who don't know how to code. But the problem with it is very hard to do anything advanced with it. Now, does that mean you can't? No. I've seen some pretty incredible LabVIEW programmers, but I could probably accomplish what they were doing 90% faster using actual code than what they had to do to make LabVIEW do that. So LabVIEW is an option, but I'm telling you, just learn the code. It's going to be a lot easier in the long run, and it'll apply to more things going into the future. So a program is a set of instructions that consist of three elements: variables, control structures, and commands. Variables, control structures, and commands. A variable is a temporary folder in memory that stores data. That's what a variable is. Before we can use something, we have to have a space in memory to store it, right? So I'm sure my issue, I'm out of memory in my own brain. So every time someone tells me their name, I always forget it immediately after because I have no storage available, right? I always have to delete something in order to memorize something else. It's actually, and you guys are all too young for this, but I call it the Kelly Bundy syndrome. So there was a show called Married with Children where a girl was learning all of these new things, but it turns out every time she learns something new, she forgets something old. I have that syndrome. So I will remember new people's names, but then I will forget all of the old people's names. I only have so much storage in here. But a variable is a temporary store. It's setting a segment of memory in our actual computer to store information. Variables are composed of data types, and data types are what is being stored in it. That can be like a string, or word, a integer, a number, or an object, a whole class of information. So a variable stores information. Before we can create anything, before I can say, hey, left motor, I want you to drive forward, I have to create a variable that represents left motor. And then I have to set the property of that left motor to say, go forward at 80% or so. Variables is what stores everything that we're working with. So when we're building our robot code, we have to create tons and tons of variables to store all of the objects that exist in our robot. All of the objects have to be created as variables. To use it, usually it's data type of what kind of variable it is, the name, and its value. We're going to get into that, but this is the standard format for a variable. You must use the correct data type for the variable that you're creating. So what that means is I can't say Falcon motor and put a Neo motor in it. It's not going to work, right? Falcon motor can only store Falcon motors. Robotics motor can only store a Neo motor. You cannot store a Falcon motor, so on and so forth. Right? There is not, because technically you're not actually putting the motors in there at all. What you're putting is the drive controllers. And the same drive controller will drive the Neo 550 or the full Neo. So here's an example. Int age equals 45. So int is an integer. You guys, you know what integer means? What does integer mean? It's a whole number. Very good. Can it be negative? Absolutely, as long as it's a whole number. Int age equals 45. So I have created a variable named age. That's the name I gave it, age. It is a data type int, integer, and I'm assigning it a value of 45. So I've created a segment in memory now. I have labeled that segment of memory age. And I've put inside it data, which is an integer number 45. I have created my first variable. Another variable here, string eye color blue. So I've created now a string variable named eye color, which has a value of blue. Now, anyone who knows programming knows that this is wrong because it should be like this. So I'm going to just correct that now. That's actually what it should look like, because what I'm putting into it is a string. Strings have to be encapsulated in quotes. Then the last one, int team number 5484. So again, I'm creating a variable that's in data type of int. Its name is team number, and what is being stored in it is 5484. All right? Yes? Yes. Now, I'm not going to dive deep into depth on it, but I use the Hungarian style coding. Hungarian style coding, what you use in Hungarian style. So let me start with the beginning. I'll just dive into it. The casing is based on generations and generations of programmers and understanding what it is that we're making. You cannot, like here I have a team number. You cannot have a variable called team number. You cannot have spaces in the names for your variables. Now, some programs let you use dashes. Some programs will let you use underscores. Some of them will only let you use letters and nothing more. It depends on the actual coding language that you're using. You cannot actually have a variable that starts with a number in FRC, in Java. So, the first coding that we saw that was widely adopted was camel case. In camel case, you take every word and make the first character capital. So you guys can look at this and it just looks like a bunch of letters, but to coders, we can read this without any hesitation because each word is identified by the first letter being capitalized. Now, the reason it's actually called Hungarian, or this is called camel case, is because it represents a camel. We got these little humps in the text. Camel case. Normally, the first thing that's listed is lowercase. Now, in Hungarian, it is a combination of data type and camel case. So in Hungarian, like for my age, that example, I would write int because it is an integer, and then age as its name. For team number, that's also an int, so I would write it out like this. So I add the data type to the left, and then capitalize each word after that. String, which is actually str in code. What was the color? Thank you. Is how I would write it in Hungarian text. Yes. Yes, I was. I'm old. My very first computer was actually an Atari, which a lot of people don't realize Ataris made computers. And my very first hard drive, I actually don't remember which one. It's the one that had a cassette tape as a hard drive. And I programmed my very first application when I was 5. Now, my dad was a programmer, so he taught me. But I programmed my very first, it was actually a Star Trek game that I programmed, all ANSI based, so text adventure when I was 5. And I was really, really upset when the tape player ate my tape. For us old people, them eating our cassette tapes was a common thing. Well, when that happens to a binary tape, it kills your program. Though an audio tape, you could kind of straighten it out, and there's little hiccups here and there. Those bends and scrapes on the tape destroyed your program because you lost segments of ones and zeros. And so the program was just corrupted after that. Sad times. Then they came out with the 5 1/4 inch floppies, were so much better. I never had the 8-inch one. Yeah. But this is that format. So yes, why is it written that way? Because I didn't include the data types in the front of these because I didn't want to confuse you guys yet. But in my mind, I was still using the camel case for the names. So the whole reason behind it is to make it easier to read.
So the difference between Hungarian and camel case is only the last word is that one?
The difference between Hungarian and camel case is the data type being added to the beginning of the variable. So this is camel case. This is Hungarian. because I started all of the names of the variables with the data type it is as part of its name. So if I were to go and change this to be Hungarian, it would look like this. It would look like that now, if I were to go through and change it. Now this is written in Hungarian. And programmers are a stickler for what format that you are using, and if you do this professionally, you have to follow whatever the lead programmer tells you to do. And everyone has their own preferences. Fortunately, I'm the boss, and so I can tell my programmers exactly how they have to all use Hungarian. They're required. So having the same format and all the students following the same format is very important. Very important.
For ease of use, or is it actually function?
It is, well, so the Hungarian gives us two aspects. One, it tells us the data type that it's supposed to be. And the next part is it's a very easy to understand of what it's being used for when we're naming it. Now, age, I could name this whatever I want. I could name it anything I want. But you should always be naming your variables what it's being used for, right? If the variable that you're creating is for the left motor of your robot, call it left motor. Don't call it something weird. Call it left motor. If it's for the right motor, call it right motor. If it's for your sensor, call it, sensor, arm sensor, or something to the sort. Make it something that's simple and easy to understand. That way, when you're coding and you start typing, you can start to guess, even though you don't remember what it is, you can start to guess what I probably called it. Now, sometimes our robots change over time and we end up modifying it, never changing the variable names. That happens. And when I have free time, I will go through and update it everywhere that it needs to be updated. But for the most part, if you named it right to begin with, you're never going to have to worry about it. You always know what it is. You always know what it is. Especially with Hungarian, if I'm, let's say, pulling up a motor ID number, I know it's going to be an integer. I type INT, and Visual Code will show me all the variables that start with INT right off the bat, and what's called IntelliSense. So it makes it so much easier to program with. When you're working with an application that has millions of lines of code, it just narrows down all of the variables as you're typing that you're probably looking for. You get down to the one, you can just hit tab and it finishes typing out the rest of it for you. It's really nice. All right, so that's a variable. We have talked about one of the aspects. Now let's talk about control structures. Control structures are how we decide on what to do based on a condition. So control structures are used to determine how the computer will respond based on a condition that's happening in our robot. Here's an example. This is called a decision structure. In a decision structure, I'm going to say if, and then I'm going to pass in a condition. If your age is less than 20, and I have a compound question here, so and is the code for and. So the and symbol means and. Your age is greater than 12, then I'm going to execute this set of instructions. Else, I'm going to execute this. So in this structure, I'm asking what is called a Boolean question. I'm asking a true or false question. Is your age less than 20? If the answer is true, it'll then go to the next question and say, is your age greater than 12? If the answer is true, it'll evaluate these together. If left is true and right is true, then our expression is true. If our expression is true, I will execute the code inside the if statement. If either of these are false, then it'll go down and execute the alternate execution. And that's the else statement. That's really, really important. You're going to use this structure a lot in your code. If driver1 dot button B equals true, I don't know why you're laughing. Oh, dear Lord. All right, so here's an example of a real life thing. Driver 1 in this particular example, I actually always use, for simplicity of coding, the controller that is the driver 1, I name the controller driver 1. And the controller that is driver 2, I always name driver 2. That way I know what I'm referencing in my code, right? Driver 1 dot their B button. If it's true, meaning they're pressing it, then I want it to move the arm. If they let go of the button, I want it to stop the arm. That's an example of a decision structure. So we can alter our robot's behavior based on input it is receiving. Based on input it's receiving. By this, if the driver's not touching their controller, what would my robot do with its arm? It stopped, right? Because if they're not pressing the button, then the arm will be stopped. And as soon as they press the button, the arm will move. Very basic control structure. Yes? So I programmed this as methods, which we will get into. When we program in methods, we usually always leave every first letter is capitalized. We start off all of our, and this is again common things. Driver 1 technically is an object. It would have a lowercase d. And this is a method, which would have every first letter is capitalized. I'm sorry, it's so ingrained in my nature, I forget to say these parts. So driver 1 would actually be in lowercase, and methods, which we will get into, which is just basically a whole set of instructions somewhere else. That's all a method is. It's a whole set of instructions somewhere else. And I'm just saying call that method over here, or go execute the code over here is what a method is. So I don't have to write out all that code right here. And that means every time I want to use that segment of code, all I have to say is move arm, and that segment of code will be over there. I don't have to write that over and over and over again. So the last part, commands. Commands are directives to the system to do something. They're actually performing a function, performing a feat. This is where we can set variables to have values or retrieve their values. We can read sensors in, set sensors up. We can run the motors. And every command in FRC with Java will always end in a semicolon. Every command always ends in a semicolon. So if it has a semicolon at the end, it is going to be running commands. You're actually telling it to do something when you have a semicolon. If you do not have a semicolon, the build will fail, and it'll actually tell you in the window where it failed, I think you're missing a semicolon. So it will be pretty thorough that tell you what's going on. If you put a semicolon where there's not supposed to be one, it'll say, hey, I don't know where this is actually supposed to be. It won't actually build. It'll say build failed, and you have to go up and figure out where it failed. Now, Visual Studios is really great at helping us decide that. If I go back to my sandbox here, I'm just going to introduce an error. I'm going to put a semicolon right at the end of this guy. It already knows, even before I built it, hey, you've got a problem. You see that this is now in red. It's saying you have a syntax problem with your application. You have referenced something I do not know about, or you have a actual character mistake in your code itself. So it'll highlight red here, and then on the right side, I can't expand this, there'll be this line that's highlighting exactly where that error is. So if you move the scroll bar up to where that is, then you can see a squiggly line where it says, hey, there seems to be a problem literally right here. And you can correct the problem. Here I see a list of commands. If I remove the semicolon, again, we have that red line. It's now red, saying you have an error. We see this, there's in this section of code right here, there's a line of red. If I click on that, let me navigate away from it. If I click over here, it'll take me up to that section where it says, hey, it appears you're missing something. Little red squiggly. Add a semicolon, and voila, it's happy again. That's the whole point of IDEs. Now, you do not have to use Visual Studios to program your robot. If you want to, you can use Notepad. But there is no help. No help at all if there's a problem. I have seen someone who was flexing by, oh yeah, I programmed my robot in Notepad. I can run to work, but I prefer to drive. So commands are telling our robot to do something, to set a new value, or to read a value. Those are the three aspects of programming really boiled down. Here's an example of command. Leftmotor.set equals 1. So I have a variable that I created to store my left motor. It has a property called set, where I can set the power level of the motor based on a percentage. 1 meaning 100% in the forward motion, in the clockwise motion. That's an important fact. It's in the clockwise motion. -1 would be 100% in the counterclockwise motion, because my motors spin, right? So I'm telling the left motor to spin at 100%, and I'm telling the right motor to spin at -1%. Assuming we have set our robot correctly. If this motor is going this way and this motor is going this way, what is our robot going to do? It's going to spin in circles, right? Because one motor is going this way, one motor is going this way, it's just going to constantly spin in circles. Not reversing the motors correctly sometimes will actually accidentally cause this issue, because when we're actually building our robot, usually our drive motor left side is facing this way and right side is facing this way. Now clockwise is opposite directions because the motors are in opposite directions. So if I did this, our robot on the field will spin. And sometimes when you've seen a robot out on the field and just spinning, it's because of some logical error in their code that caused that. I've seen robots that drive using the gyro and if the gyro comes unplugged, the robot just spins in place. because it's trying to find its angle, but its angle never changes. So it keeps spinning to try to find its angle. It's kind of funny. I like it. It's funny whenever someone sees a robot go haywire. A lot of people are like, "Oh man," and all the programmers are like, "All right, this is either happening or this is happening. This is happening." We're always diagnosing each other's robots of what could have possibly happened for that to happen. All right. Now, how's our code organized? We're going to go into what's called code structuring. Our code is organized by nesting inside folders and into sections. They're logical constructs to organize our code into something that is usable. We in FRC, in most programming languages, but in FRC, use something called object-based coding. Everything we create is not only just a single variable, but it's a variable with properties that we can either get or set. So one thing can have lots of different properties that we can execute to actually get our robot to do something we want it to do. So here's an example. I have my robot at the very top. That's the top line of my robot. Inside my robot, I create controllers. And inside those controllers, I create each driver. How I would actually see that is robot.controllers.driver1, and then I would get to the actual properties of that variable that I created, like get left stick, which will get the value of the left stick. It should actually say like left stick X or left X. Sensors then would be robot.sensors, distance sensor, robot.motors, left motor, right motor. We're actually getting and organizing our code into sections. If we look in our sandbox here, or in our code, this is the base library for everything in our code. Here's an example of those structures. So system is a parent of Java itself. And then inside of system is an out. Inside of out is this print line. And in that print line, I can pass it in information that it can do something with. So when I go up to my robot and I start creating my items, like private, motor, controller, left motor, equals new motor controller. You don't have to follow along with this. Yeah, I know that. All right. I backed myself into a hole here. I don't actually use the built-in motor controllers. I use the Robotics ones. So I don't know the parameters I can pass into this one. Documentation is key. I don't want to install the Robotics yet because we're going to talk about libraries here in a second. So we'll get into this more as we're programming. As you do it, it will make more and more sense. Our program base. There are 4 modes in a robot. We have the actual robot mode, and that is what is executed when the robot's turned on. We have autonomous, which is the code that is executed when it's running in autonomous. Remember, autonomous is the first 15 seconds of the game. So the code that's running during autonomous. Teleop is the mode when a human driver is interacting with the robot itself. And then disabled, which is what the robot's doing when it's disabled. Now I'll tell you, in disabled mode, it will not run motor controllers. So you can only do things like turn lights on and off and stuff like that. We can change LED panels and stuff like that. We can, the bottom of our robot 2 years ago had this like little hourglass shape or LED thing on the bottom, and it would go into this rainbow mode when it was disabled, which looked really cool when it was swinging from the bar. But then our cart eventually broke those LEDs. Say what? Well, it would happen when the LEDs are on the part that sits on the part supporting the, yeah. Yes, that's true. All right. Inside of that, we have two bases that we can program our robot in. There are two separate functions that we would use in a robot: timed robot and command-based robot. If you're new at programming, use timed. Okay? Time is much easier to use and understand. The problem with timed is you can only do one thing at a time in a timed robot. You can only do one thing at a time. Command is much harder to program, but it lets you multitask. Your robot can take in multiple different sensors and move multiple different motors all at the same time based on something that's happening with the robot. We actually had a very, very successful autonomous last year based on multiple commands. I think during our autonomous we had 6 commands all running at the same time to make the robot do what it did. So those are the two bases. In Visual Studios, when we create a new project and we create a template, Java, it asks you, do you want a command robot or a timed robot? It actually asks you which one. Rami's that small little one that you can get. They also have a skeleton. I'm just gonna give you a blank form or blank Visual Studios to work with. You put everything in it yourself. They also have a skeleton version of time and a skeleton version of command. I suggest just use the timed robot and the time command. Those are the two that you're going to be working with. When you start off and you're playing, timed is the easiest way to go. If you got a robot that you're building that has lots of different sensors and lots of different auto functions, command is the way you're going to end up going. So make a decision based on what your robot's going to do. In the end, you're always going to want to use command because you're never going to be like, you know what, this year I want my robot to just drive, that's it. Then yeah, you can just go straight to, time, right? But if you want your robot to get things there by itself, then you're going to end up using command because command gives you the ability to do multiple things at the same time. Now, I say that, but there's one thing you need to know. The periodic table, which is how often it runs through your code, in those 4 sections we talked about, teleop, autonomous, disabled, and the robot itself, it runs through that code 200 times a second. So technically, it can look like in a timed robot, it's doing multiple things at the same time. It's not. But it's making 200, it's going through your code 200 times a second. It looks like it. It kind of looks like it is. It looks like you're moving that arm and moving the robot forward at the same time when technically it's doing this so fast that you can't tell. Pretty cool stuff. 200 times a second. So in a time robot, it is recommended for beginners. It's very, very simple to understand. And what we're going to be building today is time robot. In the next session in advanced programming, we're going to talk about command-based. It is simple to use, and it checks the state of your inputs and sets the outputs each periodic run through, which happens how many times? 200 times a second. So, creating a time robot and navigating around. So, I created a timed robot, and I think you guys all did here too. We did that earlier. But again, just to refresh, you're going to go to that W, click Create a Project. You would select your template. We want programming language to be Java, and we would select timed robot. Select a folder to put it in. Give it a name. Put in your team number. This has to be the same number that is configured on your RoboRio that you're going to be pushing it to. And then click Generate Project. Once you do that, you're going to get this base code generated for you. This is the base code that is generated for you. So, the next thing that we want to do is add what is called the vendor libraries that you're going to be using in your code, in your robot itself. So, our team does not have any Falcons. One day I would love some Falcons, but man, they are expensive. They are very expensive. The main reason that Falcons are so expensive is that they include the motor and the controller, motor controller is all built in one device. That's really handy because there's less devices to wire and less connections to get disconnected. But it also means that the most expensive part of a motor assembly is the controller. And if the motor goes bad, guess what else you lose? The controller also, right? How often do Falcons go bad? I cannot answer. I have no idea. And it could be that they last all season, never have a problem. But if they did, you would lose the entire assembly and have to replace the whole assembly. Rev, the motors and the controllers are separate pieces. So I can just simply pop off the motor, pop on a new motor, and I'm good to go. I actually don't have to reprogram anything because the controller is still there. So it makes it very easy for an engineer to replace a motor without a programmer programming that motor, because I'm just physically swapping out that physical item at that point. So what we have here is, in our shop, is the Rev motors. So we need to get the vendor libraries for the objects that we want to use in our robot. Easiest way to do that. Can any of you guess what document website would I go to get information about my robot in FRC that we've talked about today already? Definitely not Chief Delphi. Chief Delphi is great for posting your question and getting one great response. Yeah. Yes. Say one more time. Yes, the WPI library. Yes. WPI library is where we're going to go. In the WPI libraries, you will find under the programming basics, they moved it. I just need to find it real quick. Oh, it's right here. All right, it's under support resources. Oh no, it's, where is it? They moved it. For the longest time, you actually had to go and find them for yourself. but then WPI actually added the links to their documentation, which I can't, it used to be called third party. What did you say? These are, so this is, I'm glad they added this too. These are actually example projects to show you how to use. They actually built in Visual Code all of the examples on how to use every piece of their equipment. You don't have to figure any of this stuff out. Most of all the manufacturers have actually built in built projects that you can just download from GitHub that show you how to use those hardware devices. But it's not showing me. No, I know it's in here. Okay, so under Programming Basics, the section VS Code Overview, there's a section called Third-Party Libraries. I want you guys to follow along with this example with me here. So on the Docs library, go to the Programming Basics VS Code Overview, Third-Party Libraries, and you will see all of the different libraries that you'll use in our code. So in our example, we're going to be using the Robotics, and this is their library. So if I highlight this URL and copy it, what I'm going to do is now install it as a library in my code base. Every time I create a new project, I have to actually install those libraries in my project. So I'm going to go and type manage vendor libraries. We want to manage our vendor libraries. And I want to install a new library online. Now, there's a thing between those two, online and offline. When you install a library online, it assumes that you are connected to the internet. The one problem with doing it that way is when you get to competition, you can't check for updates because you are not connected to the internet. Now, you can download all of those libraries, put them into the offline folder, and say install from an offline location. I personally still use the online. If I need to download the libraries, I will connect my laptop to my cell phone and download it using the cell phone. That's how I do it. We're all connected to the internet, so we're just going to make this simple, and we're going to install it using an online. So I want to install a new library online. Oh, sorry. So click on the W again at the top. And you may not see it, so if you type manage, it'll limit down that list and show you manage vendor libraries. So you click on that, and then we want to install a new library online. We're going to paste in that URL that we copied off the site and hit enter. And it says, hey, we recommend that you build after installing this new library to make sure everything's okay. Yep, go ahead and build. It's now going to run, and recompile the application with our new library that we just added. Build successful. Now, on the left-hand side of our navigation, you will see this folder here called vendor depths. If you open this up, you will see the libraries that are installed on your computer. Even WPI and their new command structures is a library that's inside of it. And now we have the Rev library installed on our system. So we can use in our code all the Rev objects. So if I come down here, private Rev. I already forgot what the library name is for the Spark Max. Say again? Don't worry. Don't worry about this part right here. I'm just showing you an example. I mean, here you can see I have all of these. Oh, is it just Spark? It's just Spark. I thought it was Spark Max. Yes. No, it's not Spark. I know it's Spark Max. But I have all these Spark Maxes, and if you look to the right, it's telling you that the code base that's coming from is the com.rev robotics library. That's where it's actually coming from. So I now have successfully installed that library and can use it. What's the question? Yeah. I can't hear you. Yes. All right, so we have our vendor libraries installed that we want to use with our robot. Let's navigate through this code and take a look at everything in our code. Now remember the 4 sections that I talked about, right? We have robot at the top, and inside we have robot int, robot periodic, then we have autonomous int, autonomous periodic, teleop int, teleop periodic, disabled int, disabled periodic, and test and simulation. These are our groups. Int is on initialization, is what it stands for. Any code that's inside this section will execute once when the robot's turned on. That's it. All the code that's inside here will only execute the one time the robot starts up. But then we have periodic. Periodic runs on that schedule that we talked about, the 200 times per second. Periodic will run all of the code inside this section 200 times a second. Any code that you put inside of here. Same with autonomous int. Autonomous int will run any code that's in here when autonomous mode starts. But it'll only run it once. It'll run all the code in here once when autonomous starts.
What would be an example of code that you would have in there that you need once, like go forward?
Select the autonomous mode to run. So the go forward, we would not want to put in int because it'll stop. It'll immediately stop because it'll only execute the code in there. Now, if you do put it in the wrong, if you say go forward, or if you say motors drive forward at 100% in int, it's going to drive 100% and never stop. It's going to execute everything that's in here once, and it's never going to check it again. Right. An example. So let me actually make an example of that. It's perfect. Motor we would never say motor just drive forward. We would say like if time is greater than 5 seconds, or actually less than is what we would want, then motors dot set 1 as an example. Now, if I were to put that in my autonomous int, well, it's going to say time is definitely less than 5 seconds, so it's going to set the motors to 100%. Oh, but we would also have else motors dot stop, right? The problem is it's only going to run this code once, and when it went through it one time, time was less than 5 seconds. So it'll never run through that code again, hence it'll never get to the stop. So it'll just keep running endlessly because it's not checking the code continuously. So here would be a very bad place to put your autonomous code. Where you would want to place your autonomous code here is in autonomous, periodic. Now it's going to keep going through it. And it's going to set the motor to be, run full force at 5 seconds. Just FYI, full force at 5 seconds, you're going to be hitting the alliance wall. Just FYI. But run for 5 seconds, and then after 5 seconds, it'll stop the motors. This, it'll keep evaluating over and over again, 200 times a second. If you put it up here, it'll run and never stop. And I have seen some autonomouses that failed spectacularly because they were in int. So it wasn't continuously being evaluated. All right? So int, I run it once and I'm done. Periodic, I keep running it over and over again while it's in that mode. Now, once we leave autonomous and start teleop, it's no longer going to check the code in autonomous anymore. So when I switch from autonomous to teleop, I'm now going to run teleop int once. And then I'm going to run periodic over and over and over and over again. All of those things over and over and over again. Make sense? Like an example of what a lot of people will do in teleop int is maybe reset the encoders on their motors or something like that when it starts. Or in autonomous, some people proactively will reset all of their encoders on autonomous start, which is important if you're one of the teams, which we've learned not to do, but if you're one of the teams that turns on the robot and then pushes it around, you're changing the encoder values on your wheels. Right? So when you say go and you tell it to drive, 100, ticks, it's like, oh wait, I'm way past that, and it drives backwards instead. Right? So you have one of two ways to avoid that. Do not turn your robot on until you actually are ready to turn it on. It's in place and set up and ready to go. Or I do both. Reset those encoders on start, so I know I'm starting from the position of 0 that I'm working with. We actually have on our autonomous int, we reset. I didn't actually. I should have had that. I didn't realize why I didn't put that in there to begin with. On autonomous int, I should have reset the gyro to 0. It had nothing to do with, well, never mind. No, we just had to keep restarting the code. If I put it in teleop int or autonomous int, no, teleop int would have been bad. Autonomous int would have been okay. It would have reset its 0 heading wherever we set it up. Yeah. Say what? Yes, but if, let's say we set it up wrong, we could just turn it to be the right direction and then start a, no, that would be a pain in the butt. No, that's the only way to do it. Never mind. Sorry, I was actually troubleshooting last year's robot in my head already. Yes, yes. I was thinking through the process. No, we had to do it the way we're doing it. So the things to remember is int is the start of that mode, and periodic is what keeps running that mode. Okay? Even in command base, you have an int and a periodic, even in command base, where those are being taking place. So when we're running or writing our code, this would be an example of move across the line. Except we wouldn't want to run it for 5 seconds. We probably want to run it for 2 seconds. And we're definitely not going to run it at full power. We're going to run it at probably 30% power. So our motor speeds are on percentages. 1, 100%, -1, opposite, reverse, 100%. Anywhere in between that, those decimals in between that is the power percentage levels. So that's where we want to put our stuff. Now so that is literally everything in Timed Robot is in this one file right here. Everything we're making in Timed Robot is in this one file. Under vendor depths, we have our libraries that we've installed. And if you've gone through and made the mistake of setting the wrong team number, if you go to the WPI library and the preferences, you can change the team number right here. That's where you would go and change your team number.
Now that's not by computer, that's by your, like mine, because I'm cassette on here. So like he has one of my computers.
It's by
It's by user.
well,
So
it's
he logs onto a different computer, onto his Visual Studio, and puts in his stuff, it's gonna have his team number, not my team.
yes, except unless you guys are using the same Git repository, then you're all using the same thing.
Okay.
So if you're doing it properly, you all are accessing the same GitHub repository and working on the same code base. Now, if you're working on independent projects, no, it's that team number is set per project, not even per laptop or per user.
Okay.
It's per project you set that team number.
So right now, when we're in class with you, should we be the team member?
You can be whatever you want. The trick is if you want your code to work on one of our robots and our RoboRios are programmed with team number 5484, your code has to say 5484 for it to respond. And that's the only reason that team number is in there, is the robot will respond to the same team code. It would be really bad if I pushed my code to some other robot. It could possibly do lots of damage if it worked at all. Most likely it would just keep crashing. Hopefully that's what it does. All right, so that was timed. Command-based programming I recommend for advanced users. We want command-based allows us to use commands that have really complex instructions to be executed based on a scenario or sensor or event that is happening. It allows us to do multiple things at the same time and have very complex scenarios for our robots to actually run. That's command-based. And we will talk about command-based in the advanced programming. Vendor libraries we just talked about. So in vendor libraries, we're going to install the actual libraries from other vendors into our code for the hardware that we are using. If you use mostly Rev products like a Rev pneumatics hub, a Rev motors and controllers, then you can install Rev library and you're good to go. If you're going to use anybody else, the CTRE products, install the CTRE products library. In essence, honestly, it does you no harm to install all the libraries if you want to. Install all the libraries, they're all there, they're all ready to go. But you only need the libraries for the hardware that you actually have on your robot. And I showed you guys how to add a vendor library. Now we need to add something that our head coach says all the time, make it go. How do we get our robot moving? So there are two different types of motor controllers that we can actually have in our robot. There are PWM, which is a signaling that tells our motor how fast to run. And then there is CAN. CAN is what you're going to find all higher end teams using. CAN gives us a lot more control over the motor and information coming back to us about what the motor's doing, including stuff as simple as what is the temperature of the motor? Is it overheating? And things like that. In order to do that, we have to set up IDs for everything. So we have to go through, use the software that came from the vendor, and actually program the ID numbers into all of the devices that we are working with. Then we need to capture the human controllers that we are plugging into our computer. We need to set up the drive base code for actually making the computer drive or a robot drive. And then we have to set the motor speed. By default, if you just tie a controller into directly driving our motor, it's going to drive at 100% power. There are very few drivers that can actually run the robot at 100%. They tend to break things, run into things, do a whole bunch of damage. The last 2 years, I've actually had drivers that have actually run pretty good at almost full power on the robot. There's also an advantage of not running at full power. That's when you're drawing a crap load of amperage, and you might run the risk of flipping breakers if you have too many motors, or browning out your robot more than anything. Browning it out so it resets on the field. So we are going to build, in our first project, a tank drive robot. Ooh. We're going to make it simple. Two motors. One on each side. Was it the team you helped? Nothing. All right. So the first step in setting up our robot to drive as a tank. Now these are, we're doing absolute minimums as far as what to do with our robot. We're setting up the absolute minimums for everything. You're going to want to think more thoroughly through this as you're going through it. We're going to just make it as simple as possible. I'm going to start off by getting rid of all these green parts here. They're comments. I'm actually going to remove the comments so I have more screen room to work with here. I'm in the robot.java section of our code. But I'm just going to remove all these green parts. You can leave them in if you like. I'm going to remove them just to make more room on my screen here. Just the big sections. All right, that's enough for now. All right, at the top, where my robot is started, here's where I want to create all my devices. So we are, in our example, we installed the Rev Robotics library. We're going to use Rev Robotics motors and controllers. So I'm going to create, we're all in one class, so I'm marking everything as private. Private, there's two different functions that we can use, private or public. Private or public specifies who can access this object outside of the object. If it is private, it's only accessible inside this object. If it is public, it's accessible outside of this object. In Time Robot, we're going to use private for everything because we're only inside this project. When we move to command line, we have to be actually very mindful if we're making something private or public. And we'll talk about that when we get to that advanced class. So I'm going to make a private CAN Spark Max. This is the drive controller for Rev Robotics. And you notice it's green. The reason it's green is that is its data type. Remember when we talked about data types? What can actually be stored? CanSpark Max is actually a data type. It's an object. And it's green because it's saying, hey, I'm getting this from a library. So CanSpark Max, let's name this left motor. So I'm giving it now a name. And I'm going to... Okay. All right, so now we need to...
Green because
It's part of a library. It's a keyword. So now we need to instantiate it. We need to actually make it into an object. So we have a variable to store an object. We need to create an object to store in it. So this word, that a keyword called new comes in. I'm going to create a new object, and it is of type CanSpark Max, and it has something called IntelliSense that it starts kind of filling this stuff out for you. What ID have you programmed onto this controller? I'm going to say I programmed it. I never start off with 0. So this is CanID number 1. Whenever I see 0, I know it hasn't actually been set yet. So I always change everything to start with at least 1. So this is device ID number 1. And the next question it's going to ask you is, what kind of motor do you have plugged in to this controller? I have a K motor or motor type dot K. Our options are brushed or brushless. So if we are using a Neo, it is a brushless motor. We learned about the difference between brushed and brushless motors in the last class. We're going to use a brushless motor because a brushless motor gives us lots of encoders and feedback about what's going on with the motor that we can actually program to. So we're going to use a brushless motor. And this is a command. What do I put at the end of all commands? Semicolon. We have our first motor. Woo! No one else is excited. Say again?
where'd the K come from?
That is what they use in their library. K is often in coding represented as a constant. Something that is read-only, you can't alter it. I know constant actually starts with C. Why did someone make it a K in coding? I don't know. But it's what we all follow to this day. It just means it's a constant. All right, so we got a left motor. What else do we need? We need a right motor. So that's private. CanSpark Max right motor equals new CanSpark Max. And it's going to be the next ID, which is probably 2. Does it have to be 1 or 2? No, it could pretty much be any number you programmed into it. And I'm trying to remember if there's a limit. Was there? I think there was a limit of 99. There's 100 IDs, I believe. Can't hold me to that. I don't remember. I've never even tried to set a really high number, but you can. Then the motor type that's plugged into this is a brushless motor. Semicolon. Woohoo! We got 2 motors. Now, there are a whole bunch of different drive bases that I can use with our robot systems. We have tank drive, we have swerve, we have mechanism, and differential. It's not actually tank drive, it's differential, mechanism, swerve are the 3 types that we can actually use. I don't think there's any other type. I think that's it. We are going to be using a differential drive. So we want to create a private differential drive. And let's call this just drive. New differential drive. And what does the differential drive ask you for? What is the left motor and what is the right motor? Well, I'm just going to pass in those motors. So I'm going to pass in left motor and right motor. I now have a differential drive system. Woo! We're almost done programming a robot already.
Why does it say differential?
So what? All right, so now we have our differential drive. We need a way of actually driving it, right? So we need a controller. Now, there are tons of different controllers that you can use for driving. We typically always have our drivers use Xbox controllers because they're very familiar with them, except our primary driver who doesn't game somehow is our driver. She has a controller now, and she still doesn't game with it. It just collects dust. So we typically use Xbox controllers, and they have programmed an Xbox controller library for us. So we don't have to actually do everything from scratch. So, all right, so we're going to then create an Xbox controller that's tied to our driver. So we're going to create a private Xbox controller, and let's call this driver 1. And new Xbox controller. And it's going to ask, what port is it plugged into? The very first port that we get on our driver station is port 0. So I'm going to say yes. The primary driver, driver 1, is plugged into the first spot on our system. And it's not dependent on the USB you plug it into. It is dependent on the sorting order in the driver station. Something we talked about in the control systems last week, or last month. Oh, it's been a month. So we've got the primary components we need to drive our robot. So let's come down here. Should we put our components in autonomous? Nope. Nope. Now, technically, you can technically do that, but if you touch your controller during autonomous, we're obviously not going to put it in there. We are going to go into our teleop, and inside the squiggly, we're going to add the code to make it actually drive based on the driver's command. So we have to tell our drive subsystem, which was a differential drive. What did we call it? We called it drive, right? We're going to take drive, and it's going to give us the option of using arcade drive, tank drive. Actually, don't remember what the other drives are. Oh, it's arcade and tank. Those are your two choices. Arcade drive means I'm going to use one side for speed, one parameter for speed, and one parameter for rotation. So if you're using a joystick that's like this and turns like this, you would use arcade drive because you're using an arcade stick, right? We're not going to use arcade drive. We're going to use tank drive. Tank drive assumes that you have two sticks that you can use, like driving an actual tank, right? A tank has two sticks. Modern day tanks don't. Old tanks do. And if I want to turn, I do this, and then I do this, and so on and so forth, right? That's tank drive. We actually will drive that way, our robot that way. So we're going to do tank drive, but instead of using two sticks, we're going to use our sticks on our Xbox controller. So I'm going to take driver 1, and get, for the left side, I'm going to get the left Y, because that's up and down. And for the right side of the tank, I'm going to take the driver 1 dot get right Y. So the left Y and the right Y on our sticks. Everyone got that so far? Now I'll tell you, this is really all you need. You can now drive the robot. This is all you need. Now, in real life, it's not going to go how you think it will, because there's a few things that we need to set up also. But that is the basic functionality. That's all we need to actually make it drive and move. The next thing we need to do is actually set up for a robot that, remember in tank drive, normally when we're installing the motors, they're installed in different directions, right? So one means clockwise, but if they're installed in opposite directions, that means one motor is driving that way, one motor is driving this way in the one position. So what we actually want to do is invert one of the motors, saying 1 should actually be -1, and -1 should actually be 1. I'm going to invert the values. So I'm going to take my right side, which is backwards, and set inverted is true. I'm going to tell the right side that it's inverted. It's installed backwards. And I'm doing that under the robot int, because I'm only going to set that value once when the robot starts. Everyone have that? Under robot int, I set the right motor to inverted, so it spins in the opposite direction. Now, the next thing we need to talk about is the controllers itself. I cannot actually remember which side, but on an Xbox controller, it's either the left stick or the right stick. I think it's the left stick is inverted on the controller itself. Meaning when you push up on it, it actually gives you a -1 value. When you pull down, it gives you a +1. So we need to actually invert the sticks also. So if we go down to our tank drive, and I need the value of the stick on the left to be inverted, you simply add a negative, a dash, in front of it. It will actually give you, thank you, it will give you, or it'll invert the value that's being passed in. I'm actually going to plug in this controller, which I have no more USB ports. I'm not going to plug in this controller. We showed in the last one how to open up the game tools, and you can actually see in the game tools the direction the stick moves, or the value it gives you when you move it. That's an easy way to see if your stick is performing in that function. If your stick, when you push forward, is not a +1, you want to invert that stick. Now that we've done that, we have voila, a functioning rolling robot. So now that we have a robot, we want to give it the ability to see. So we have the I can see sensors, programming sensors into our robot. The first thing we want to add into our robot is limit switches. Limit switches make sure that we don't take in too far, or we don't, when this lever cuts over to this, we don't go past that, so on and so forth. Those are called our limits, our robot limits. And we can actually add limit switches in order to limit the programming movement of our robot. We've talked about those limit switches and how to connect them into our RoboRio so we can actually code to them, but let's actually look at coding them. So in our code, at the top here, in the robot extends timed robot, we want to add another new object. This new object I'm going to add is a digital input. A digital input, because it plugs into the DIO on our RoboRio. So it's a digital input. I'm going to call it something like my limit. And this is a new digital input plugged into channel 0. Excellent. So I've created a new, did I start the recording? Yes. I created a new limit switch that my robot can now use. Now I have to install this in the right spot. We're going to use this as an example. It's like there's a limit switch on the front of the bumper. You technically cannot do that. But let's pretend there's a limit switch on the front of our bumper, and I don't want it to drive anymore once it's hit that limit switch. I want it to stop. So I've created a limit switch. Go down to my periodic. And here we do have our code for our driving, right? But what if I don't want them to drive if the limit switch is activated? I need to write a control structure, a decision structure. I'm going to write my first if. If my limit.get means gets the value of limit. If I've reached my limit, I want to stop the motors. Else, let the driver drive the robot. So now I created a decision structure to test something. And if that something is true, do something about it. Else, let it sit and do the thing it was doing. All right, so the next kind of sensor that we can program is a distance sensor. A distance sensor allows us to see how close we are to an object. So we can measure it. The example we're going to use here is an ultrasonic sensor. But anything made by any device that we can use in robotics will have detailed documentation on actually how to use that. Where do we go to see that detailed documentation? Docs, WPI library. And once I'm here at the WPI library, I'm just going to type ultrasonic. And here, it gives us the instructions about ultrasonic. Let me go up here to digital inputs. Digital inputs is our limit switches. And we can see it showing us where we plug it into our RoboRio, how it plugs in, how you wire it up, as an optical encoder. And then in the examples, it doesn't actually have one for a limit switch. I guess that's too basic. Yeah, it does have it for ultrasonic. Yeah, I guess limit switches are too basic that they don't actually have code for it. Because literally what I just showed you is all you need to use the limit switch. But if we do, I'm going to open those up in a separate tab as an example, but it would help if I spelled it right. If I do ultrasonic, it's going to show you again. Now, an ultrasonic sensor is an analog sensor. It'll give you a reading of 0 to 5 volts. In between those, 0 to 5 volts. Meaning at 0, you are right against the target. The higher the voltage, the further away you are from the target. And I might be backwards in that. I don't know. You'll have to plug in your sensor to find out if it's opposite. When you're really close, it's full 5 volts. When you're really far, it's 0 volts, one of the two. You have to play with it, plug it in and test it. But it'll actually show you, this is for that MB1013 sensor, which is the one I showed you in the control systems. Here is the plug-in for the ultrasonic rangefinder from Vex. This is that sensor that I showed you. And you can go to the examples. If I go to the robot code on the examples, it will show us the details of the sensor. So here it's the 2 ports it's plugged into. And then rangefinder. Yeah, they called this ultrasonic sensor the rangefinder. And I can get the rangefinder in inches or millimeters. And I can make now decisions based on the distance I am from an object. Now, the caveat with you using ultrasonic sensors is ultrasonic sensors interfere with each other. So if you have an ultrasonic sensor and the robot next to you has an ultrasonic sensor and they bounce into each other, we got a problem. So ultrasonic sensors are usually good when there's nothing going to be in your way. So if I need to be this far from this wall in order to shoot, good source for an ultrasonic sensor. But if I need to see across the field, probably a bad thing to use an ultrasonic sensor for, because a lot of objects can get in your way during that time. So we don't want to use it for that. Close proximity targets, ultrasonic sensors are great for. And this is the WPI example libraries. If you go here, it actually has examples of all of the different things that are common with our robots. Lots and lots and lots of examples. So this is an ultrasonic PID. So this is an ultrasonic sensor with a PID controller. A PID controller is what we use for automation. If I wanted to automatically find this distance, meaning I wanted to automatically move the robot based on if it's far enough or not, this will actually introduce the code to actually move the robot based on its range. So I'm going to move the robot based on its calculation of how far it is from the object. That's how we do autonomous. We use PIDs. All examples in the library for you to consume. I didn't know all of this stuff right off the hand. I had to constantly look at these libraries and then play with it until it worked for us. You're going to have to do the same thing. Now, you have the benefit that when you run into a problem, you can call me and I can help you. I just had to cry myself to sleep, that's all. But all your examples are in here. Now, most of the vendors all have examples. If we go to the Rev Robotics, software, we can actually see here in their GitHub all of the examples for all of the hardware they sell. So we can get detailed information and examples on exactly how to use their stuff. Really, really useful. Really useful as a starting point. And that is an ultrasonic sensor and how we get it to move based on that. Full of hot air, pneumatics. You what? Yes, but when you compress it, it's going to get hot. So, programming objects. There are two objects that we have to work with pneumatics in our robot. We have the pneumatic controller itself, and then we have the solenoid that actually performs the action. We learned about those two hardware pieces in the last module. But let's program pneumatics. So we're going to go back into our sandbox. And we need to add a new device. So we're going to add a new device. So I'm adding a new compressor. I'm just calling it compressor. And when I instantiate it, it asks me what type of compressor is it. The pneumatics module type is either the CTRE PCM or the Rev PH. It can only be one of those two, because those are the only two that are legal in FRC. They're the only controllers you can use. I prefer the Rev PH because it has twice as many solenoid controls than the CTRE does. And the Rev pneumatic module gives me the ability of having an analog sensor so I can actually measure how much air is stored in the tanks. Really, really useful information. So I'm going to use the Rev pneumatics module. Need to shrink this up just a little bit. There we go. So I'm going to create a new compressor. I'm going to call it compressor. Here, we'll make it my compressor. It's a new compressor, and it's using the Rev PH controller. So now I have the controller. I need now a solenoid to actuate. So let's create another object. Private solenoid. My solenoid. New solenoid. And then I specify what channel it's plugged into. Sure. The first channel, which is channel 0 on the system. So now that I have a solenoid to use, let's use it. I'm going to come back down to teleop. And I'll pause the recording and go back up to the top so you can see the top again here in a second. What I want to do is program it to where I can actually actuate the solenoid. So who's going to be the one doing the actuation? It's going to be our driver, right? We could do it by code based on the time. Every 5 seconds, actuate. But it's more logical that we're going to use our driver. So I'm going to take driver and let's get the A button. When they actuate, if driver 1 presses the A button, then I want solenoid oh, sorry, not solenoid, my solenoid dot to close. Else, I want my solenoid dot to they don't have it open. You just have to use set. Set to true. I'm gonna actually, so we don't get confused here, dot set to false. So when they press the A button, it'll set the solenoid to false. When the A button is not pressed, it'll set the solenoid to true. So actuate in one direction, actuate in the other direction. And like that, I now have control over pneumatics. The funny part is pneumatics is very, very complicated to set up on your robot and get right. It's really, really, really easy to program. Getting pneumatics to do something it inherently doesn't do is quite hard. I want you to stop halfway right here. Use two solenoids. Use a what? I don't know what that one is. Is it legal? Is it legal? Oh, then yeah. Oh, well, there you go. I have seen teams that have a beautiful stop point. They actually achieve it by putting two cylinders to each other. So extending one gets them to that one point, then they extend the other to get it to completely. Drive yourself autonomous. So move off the line dead code. We're doing a simple autonomous. And the simple autonomous is just to move off that line. How do we do that? Well, we move off our line using our drive motor, right? Our differential drive that we've programmed. So there are a couple things that we need. If I just come in here and say, hey, autonomous, I want you to drive tank, set it to 1 and 1. That is my autonomous. I put it right in there. During periodic, drive forward. Anyone see a problem with this particular autonomous? Nope, it won't spin. First, let's analyze this. How long does autonomous last? 15 seconds. So how long is this autonomous going to run for? 15 seconds. And at what speed did I tell it to drive at? Full speed. It's going to drive at full speed for 15 seconds. It's going to drive through the other alliance wall. Actually, it won't. It'll stop. The alliance walls are really strong. What? Yeah, I don't think it would take that long, but yeah, in a couple of seconds, it's going to hit that other side. So obviously, that is not a good move off the line, right? So we want to introduce a time element into our command. So I'm going to use a stopwatch. Let's go back up to the top again here. And I'm going to create a private timer. My timer equals new timer. So I'm going to create a timer. Now this is where we're going to get into using those int. See that autonomous int up here at the top? I'm going to come down here. I'm going to use that timer. That timer is created, but it's not running yet. This is where we want to execute code once not over and over and over again, right? So I'm going to set my timer to start. And actually, before I do that, I'm going to do my timer dot reset. So I'm going to reset the timer, and then I'm going to start. I want it to start counting. I want it to start counting. So now I'm going to go down to my autonomous, and instead of telling it to drive straight and continuously, I'm going to say if, we got another decision structure, right? If my timer dot get is greater than 2 seconds, it's in seconds, by the way, drive forward, and I probably really don't want to drive that fast. Let's say drive at 30% for 2 seconds. Oh, my logic is backwards. I want it to drive while the timer is less than 2 seconds. Now here's the problem, is I told it to drive at 30% while it's less than 2 seconds. After 2 seconds has passed, what do you think our robot's going to do? It's going to keep going. Why is it going to keep going? And still, because I have to give it a command to stop. Excellent. So I need to add in an else statement to say, hey, stop. So after 2 seconds, stop. Yes?
You mentioned a good point. So it's going forward, but what you want to do in reverse, do the opposite, anything else in it?
To cross the line and then come back?
No, then you stop it. Stop is an inertia, you got the negative control.
Actually, it depends on if you have the robot set in braking mode or not. But yes, you need to constantly test your code to see for any unexpected outcomes. So now we're using a timer to test and tell it to run forward for 2 seconds and then stop at 30%. Oh, actually, I just made it curve, didn't I? Because I drove the left motor a little faster than the right motor, I actually just made it curve to the right. There we go. Now let's drive forward. Yes. Say again? Oh. Yes. Go back up to the timer part. Right here. All right. So now we have programmed a basic robot, or basic controllers, had a human instrument for controlling it, added in a sensor to limit its run, and added an autonomous command to make it move automatically. We've programmed all the main aspects of our robot now. I have actually seen lots of teams go into competition with that little code and be very successful. So it could take just that little amount of code and you're good to go. That is the end of the intro to coding. Yeah, I know thank you. That was a lot to learn in a very short period of time. You're going to do it and you're going to fail over and over again. The only time you truly actually fail in any of these attempts is when you give up. Okay? As long as you keep trying, you are good. And there is help for you. One of the biggest benefits to all you guys is if you need help, call me and I will help you. I can actually help you remotely too. I've helped several teams last year by terminaling into their coding computer and fixing their code for them. So call me if you need help. Chief Delphi is also a great resource for finding answers, but you do have to trudge through a lot of information and bad advice before you get to something that's valid. I commend everyone who's trying to help, but sometimes the advice they give is incorrect. So you have to be cautious about the information that you're receiving. I will not always be correct myself, especially if you show, say again? Yeah, especially if you show me a configuration I have never seen before, I'd be like, wait, but why are you doing it like that? But you have a good logical reason for it, and it happens. So there are things that I have still yet to learn. When you are coding, be safe, especially autonomous. It takes one wrong line of code, one wrong parameter, and you took an FRC robot and turned it into a battle bot. I will tell you, our team ourselves, got asked to remove all the batteries from our battery at a 4-H fair. Because something happened, we still don't exactly remember, but we're pretty sure when they turned the robot on, it was set in autonomous mode on the driver's station, and they didn't realize it. And so when they enabled the robot to show it, it took off and drove through 3 other booths before it stopped. So we were asked to take the batteries out of the robot. We were told to take the batteries out of the robot and literally take them out of the building, so we couldn't put them back in. Off the premises, yeah. So, but I know of another team that had the same circumstance, and their robot drove in the opposite direction and actually broke through the brick wall. Yeah, so be careful. Whenever you're running autonomous, the rule is everyone off the field. Because it should work. It's worked 100 times this way, but this one time, it took off. It's going to be bad. If you need help, again, my name is Roger Johnson. I'm with Team 5484. There's my email, and there's my GitHub. Feel free to go look at our code if you have any questions and you want to see how we've done it in the past. You can go look at our code. It's not brilliant code, but it's pretty effective, and we get better every year.